Hi, everybody. My name is Josh Bloom, and I'm a professor in the astronomy department. Welcome to the second incarnation of the Berkeley Data Science Lectures. For those that were here last time, know that we've been thinking hard about how data science happens on campus and even outside of campus. And what we're trying to do is engage this community in a very broad discussion, and we're doing that in today's lecture by showing you really something that's kind of at the nexus of both the physical science in statistics, computer science, basically connecting hardware, software, algorithms, and domain-specific questions into something that is very near and dear to all of our hearts here in California. So it's a pleasure to welcome Richard Allen, who is the director of the Berkeley Seismology Lab. He is also professor in the Earth and Planetary Sciences. His work really spans from trying to understand the deep processes within the Earth. Those are the processes that are responsible for plate tectonics, and also trying to understand how we detect and then classify earthquakes in a real-time environment. He's an advisor to companies such as Boeing and Google and the BART for helping them understand how to use real-time warning systems in their actual business processes. And that's been tremendously exciting, I know, for him, and very useful for those companies. He did his undergraduate work at Cambridge University, and he did his PhD at Princeton and started here in Berkeley in 2005. So one of the things that you'll hopefully hear more about, I'll just sort of tell you in case you haven't heard, is that the Governor Brown, signed a bill very recently, just this past week or even the last 48 hours, that essentially mandated that California as a state set up a earthquake early warning system. So we have a lot of people to thank for pushing on that, but I know Richard was a big part of that. And so it's a very timely discussion, both on the domain side, but also a very timely discussion for us here at Berkeley on data science. With that, I'll ask Richard to come up here and start the lecture, but I wanted to just tell everybody that this is meant to be a very interactive conversation. So please, by all means, stop our speaker, ask questions, and we'll get that conversation going. So without further ado, Richard Allen.
Great. Thank you, Josh. So yeah, as Josh just mentioned, this is part of a new sort of lecture series, and where we're trying to kind of begin to get people interacting when they talk about data science. And so I'm going to take a slightly different approach to what Josh did at the first one, in that I have sort of a talk here which is talking about the domain science that we're doing. I'm going to sort of try and illustrate why it's relevant to the data science group, but I really want people to just stop me whenever they want if they want to talk about some aspect of the data science, and I can cover as much or as little of the domain science as we have time to. Okay, so that's sort of the plan here. Okay, so I'm going to start by giving you the bottom line when it comes to talking about earthquake early warning specifically. So what is earthquake early warning? Earthquake early warning is about providing seconds to minutes worth of warning. This graphic at the top here, hopefully you can make out California on its side here, illustrates the maximum amount of warning that you can get. We're currently trying to build a system for the entire West Coast. California just stepped up to the plate on Wednesday, as Josh mentioned. But we're trying to do this for the entire West Coast. In Seattle, you could have up to 5 minutes. Gosh, you can't read that, but you could have up to 5 minutes of warning. Here in San Francisco, you can have up to about a minute's worth of warning. Los Angeles is kind of the same, about a minute's worth of warning. So that's what we're talking about. Seconds, tens of seconds, up to a minute or two worth of warning.
Sorry to interrupt.
Yeah,
So
no, cool.
Are those limits because you're assuming a single point of origin?
Yeah, so what primarily controls the amount of warning time you get is how far you are from the epicenter of the earthquake. Okay, so that's the first order control on the amount of warning. So here, for example, this is this 5 minutes worth of warning for Seattle is based on a magnitude 9 earthquake that starts at the southern end of the Cascadia subduction zone and ruptures to the north of the Cascadia subduction zone. Likewise, for San Francisco, it's a magnitude 8 that starts at the northern end of the San Andreas and ruptures down towards San Francisco. So the catch is, if that same earthquake, that magnitude 8 earthquake, starts on the San Andreas just offshore San Francisco, then San Francisco might not get 0 warning at all. But Oakland and Berkeley would get a few seconds of warning. San Jose would get 10 seconds of warning, etc., etc. Yeah, exactly.
And it's unrealistic to imagine earthquakes starting very close to Seattle? I mean, is that what?
No, the same is also possible in Seattle.
To be for this particular order.
That's right. I'm showing here the maximum amount of warning time. That's right. So this warning time is for this origin point. If for Seattle, if the origin point is here, you still actually have about a minute's worth of warning, but it's not 5 minutes worth of warning. Exactly. Yeah. Okay. Great. Keep the questions coming. Okay, so what is earthquake early warning for? So it allows individuals to kind of duck, cover, and hold on, so take individual protective measures before the shaking starts. It allows automated systems to start to slow, stop, and move things into a safe mode. It allows for situation awareness. Groups that run infrastructure over large areas, they can understand what might be causing cascading failures. And so as a result of that, it reduces the overall cost of earthquakes. It reduces the recovery time after an earthquake. So how quickly can groups get back on their feet? And I love to add this bullet here. It's a very nice demonstration of the public value of earthquake science. I always include that bullet when I'm talking to earthquake scientists. This is not a group of earthquake scientists, but given the chaos with the federal budget right now, I think this is just about as relevant for everybody. So I think it's very valuable because we can take our fundamental science and we can show the real public value of that. Now, I've spent about a decade arguing that these are valid reasons for why we should do earthquake early warning. So as Josh mentioned, it's particularly exciting that on Wednesday the governor finally signed into law a bill that has been working its way through the system for about 8 months. This was a bill that was introduced by Senator Alex Padilla in January of this year. We've come to learn a lot about the legislative process. It's just chaotic. It's unbelievable. But at the same time, this law actually passed unanimously. Both houses, both in the Senate and the Assembly, passed unanimously about 2 weeks ago, and then the governor signed it on Wednesday. So California has its own earthquake early warning law. There's a catch. There's no money. So the law says California should build an earthquake early warning system, but it does not allocate funding to do it yet.
Is it should or shall? So is it a mandate or is it a recommendation?
So what it actually calls on is it calls on the Governor's Office of Emergency Services to first put together a plan of how to implement earthquake early warning and then to identify a source of funding. And they have until January of 2016, and if they haven't done that by January of 2016, the whole thing becomes null and void. We shall see. So, we've spent, I don't know how long trying to make this happen. Hey, we're still celebrating that they signed it, okay? We can talk about these questions on Monday. But the irony here, we've been working on this very hard. Obviously, we've been pushing this forward very hard. And the reality here is now it feels like it's just a new starting line, right? Because now it's basically the same process again, but with a different group, with the Governor's Office of Emergency Services. So we will see. Okay, so...
just to bring up kind of a
Sure.
question of relevance to us in that part, to what extent do you think that having data, having analysis played a role in helping drive that through in the legislative process, or was it just simply kind of the obviousness of, oh my God, we're all going to die, we don't need data for that?
No.
So to what extent?
Sure. So basically the question is how much of a role did data play in actually making this happen? I would say a huge role. We have, as you will see in a few minutes, we have a demonstration system, earthquake early warning system, that's operating today. So some of the people in this room get alerts when there's an earthquake that's going on. And so we could actually then demonstrate that to the legislators, and that was key. There was no question. Being able to actually demonstrate this essentially, this demonstration system makes all the difference in the world. So obviously we wouldn't have that without data.
How long have you been working on this before you took it to Senator?
We've been working on this for a decade. And the way that this got to Senator Padilla, so Padilla is actually his district is San Fernando Valley. And so this is a collaborative project, as you'll see on the next slide, with Caltech. And he was actually visiting Caltech to talk about bioenergy. And while he was there, one of the legislative affairs people pitched to him, how about earthquake early warning? He got interested. He's a science grad, and it went from there. Okay, so who is doing this? This has been going on for a decade. Particularly in the last 2 years, the group that's been engaged and making this work has been growing very rapidly. And so the group as it is right now in terms of academic institutions is Berkeley, Caltech, University of Washington, ETH Zurich, and SCEC. SCEC is the Southern California Earthquake Center. The number of groups funding it has also been growing. The USGS, for the longest time, Gordon Betty Moore Foundation, Cal OES to a small amount, and hopefully Cal OES is going to become the primary funder based on Wednesday's new law. But also this group of expanding business partners, or partners who are in business, who are actually testing the system. They're also contributing to funding the system. And one of the real points I want to make here is that this project really could use input from the wide range of kind of data science specialists for reasons that hopefully will become very clear over the next few minutes. So the key points are that earthquake early warning is coming. I've been saying this for about 5 years, but it seems that much more relevant after Wednesday. But there's many challenges, and so again, this really is an invitation for people to get involved. Okay, so before I start talking about the specifics of earthquake early warning, I want to back up a little bit. Part of the purpose of this seminar is to kind of get people talking to one another so we understand what other resources there are on campus. So I have 3 slides on the Berkeley Seismological Laboratory. So of course we're based right here on the UC Berkeley campus, but what's really unique about the lab is that we run geophysical observation stations across Northern California. So this is about the 70 or so broadband seismic stations. We have one which we're particularly proud of on the ocean floor, MOBB. We also run very accurate GPS instrumentation that can actually see the movement on the faults, and then a series of borehole stations in pink where we're putting instruments actually very close to the faults. So the data from all of these sensors stream in real time back to the Berkeley Seismolab. And the purpose...
How deep is that ocean sensor?
It's on the ocean floor. The water depth there, I think, is about 1 kilometer. If I remember correctly, something like that.
Is that installed robotically? Or?
Oh yeah, it's on the end. So there's actually MBARI, the Monterey Bay Aquarium, has a cabled. The red cable, the red line you saw there is actually a cable. So they have a whole sensor system down there, and our seismometer is one of them. So it's kind of a modular type setup. You basically, you go and you make it sound far too simple. You go and you stick your instrument down and you plug into their box, and you get data back. Yeah. Okay, so that data all feeds back in real time, and so we use it for 2 purposes. We use it for real-time information, which of course is what I'm going to talk about today, but also we use it for all kinds of fundamental science. The real-time information is largely delivered through the USGS. So all of this is done in collaboration with the USGS. And so whenever there's an earthquake and they say the USGS reports that this is a magnitude 5.5 earthquake, that's actually we're providing the magnitude for these earthquakes, and the USGS is then just kind of delivering it. There's a variety of tools that we do that, of course, websites, specific tools. That we also have an app. You should all download this app and play with it, MyQuake. But then also, of course, we generate more sophisticated tools that are used by emergency response, hazard maps, shakecast, and then, of course, earthquake early warning is the new product that is in the works. But the other thing that should be interest of the data science group is the data archive. So one of the things that Berkeley really led the way on was building an archive of data, a continuous archive of data. When they started doing this, it was what was considered to be significant volumes of data. Of course, by today's standard, this is not a particularly significant volume of data. But what's important here for studies of Earth processes is it's a continuous archive that goes back about 20 years. Okay? And the data set comes from those instruments that I showed you in Northern California, but also many other instruments that you can see that are shown up here. And just for those who are interested, there's a whole variety of data access methods. I know Josh could spend this afternoon and chew his way through a large chunk of this data using one of these kinds of access tools. And of course, if people are interested, you should get in touch and we can tell you how to make use of it. Okay, so let's start talking about what it is we're actually trying to do. So the same thing that we're all trying to do is extracting the signal from the noise. And so this is about 4 days worth of data recorded at, I think it's at BKS, which is one of the instruments that's in Strawberry Canyon, just above campus. So this is sort of the modern day equivalent of the helicorder plots that you always see on the news. This is an hour worth of data, and as I say, this is about 4 days worth of data. And so, of course, we can immediately see the big signals. This is actually from this week, so that's a big teleseismic earthquake. That's actually the Pakistan earthquake a few days ago. This is another big teleseismic earthquake. It was an aftershock from that Pakistan earthquake. But you can also see some of the small local earthquakes, quite different in character compared to the large events. And then there's a lot of noise. This is pretty much all noise. This is primarily microseismic noise that's coming from ocean waves hitting the shore. In fact, we use this noise, though, to image the structure of the Earth, although it doesn't include earthquake signals. And then, of course, there's many other signals that are in between this. And the real challenge here is to be able to extract the signal from the noise. And when it comes to real-time information systems, of course, this has to be done in a completely automated fashion, and it has to be done instantaneously when it comes to earthquake early warning. And so that is what we're trying to do. Okay, so let's talk about earthquake early warning. And to do that, I want to start in Japan, and I want to start by going back 2 years. And so what happened 2 years ago, of course, was the magnitude 9 Tohoku-oki earthquake, which also created this huge tsunami. So the images that most people have in their minds from this, of course, is from the tsunami. And in fact, most of the fatalities in this particular earthquake were due to the tsunami. But this also, in fact, was a test. It was the first real test for Japan's earthquake early warning system. They turned on their earthquake early warning system in 2007, and this was the first primary test for that system. So this is a live TV broadcast from the Parliamentary building in Tokyo during that earthquake. This is the automated warning that pops up on all TV screens in Japan, also goes out over radio, and also to cell phones, at least to some cell phones. You can see that although this warning is going out, there's absolutely no reaction of anybody in the Parliament building, okay? And that is because they're not watching TV. So the cell phone warnings that went out to the people that were very close to the epicenter of the earthquake. Okay? The TV warnings went out across the country. This is the epicenter. These are the regions that they're expecting strong shaking. On this map, Tokyo is down here. Okay? So that's why their cell phones are not going off, because they're not close enough to the earthquake for the cell phone warning to go out to them. However, as you will see, and you may remember, that in fact there was strong shaking in Tokyo in this earthquake. You can see these folks are beginning to look up. That's because they're beginning to feel some very slight ground motion. Okay, but it's obviously not frightening ground motion. They're doing nothing other than looking at the lights. I'm going to back out in a minute, and you'll see there's some big chandeliers which are beginning to sway a little bit. So this is the very low amplitude energy that first radiates out from an earthquake, and they don't know whether this is just some small earthquake that's close by. That's presumably what they assume, is they're not doing anything, versus what is actually the beginnings of what was very serious ground shaking that was felt in Tokyo as well. This is as quickly as they can get a live announcer behind a TV camera. And in fact, all he's doing is reading this automated alert. And also noting that Tokyo is now beginning to shake. But still, we're about 20 seconds from when the serious shaking actually started in Tokyo. So now you can see the shake. You can see these lines are actually shaking. It's not just the camera that is shaking. So there was more than a minute between when the alert went out and when the strong shaking started in Tokyo. So what's the conclusion from this particular event? It's sort of a mixed bag. Most importantly, this was a success. They successfully detected the earthquake. For the locations that are close to the epicenter, the biggest city that's close to the epicenter is actually the city of Sendai, which is located right here. They had about 20 seconds of warning, and they did push out the warning not just to TV, but to people's cell phones. However, they underestimated the shaking which did occur in Tokyo. So that's why they didn't push out the cell phone warnings in Tokyo, because they were underestimating the shaking that was felt there. So it's a success close by, but they underestimated the shaking that's further away. Okay, so that's the challenge here, is being able to accurately characterize the earthquake in order to fully understand the shaking. Yeah?
Well, I heard one of the critique was that you might not be able to detect the earthquake, but we were not able to estimate the magnitude of the earthquake. So that gave a false signal to the population.
That's exactly right. And so depending on how time goes, I'll talk about this in more detail, but the quick answer to your question is that there were two problems with the system. One, they underestimated the magnitude, exactly as you just said. The other problem is that they treat the earthquake as being a point source. So this is the epicenter of the earthquake, and they treat the earthquake as the shaking rather, as being a simple function of distance from this point. That's what we mean by a point source. For big earthquakes like this, in fact, the earthquake ruptures long sections of faults. In this case, it was a fault that came down in this direction. And your actual intensity shaking is dependent on your distance from the fault, not your distance from the epicenter. So if the actual fault is like this, then obviously Tokyo is much closer to the fault than it is to the epicenter. So that's the second reason. Yeah. Okay.
Quick question. Were those failures and those errors due to incomplete data acquisition, incomplete data processing, or
the model?
Models?
The model.
The forward models being forward.
Entirely the model.
The forward models.
Yep. Entirely the model.
And is that lack of knowledge of the underlying physics or the boundary conditions in the subfloor and all that?
No, we understand the physics. We just hadn't. And I don't want to be too critical here because they're way ahead of us. So I say we. I mean, we understand. As I just described, we understand how to estimate the intensity shaking. It's just earthquake early warning methodologies have not yet progressed, so they are behind our understanding of the physics, the methodologies. Yeah. Okay. So where are we in California? So today, as I mentioned, we have a demonstration system. It's delivering alerts to a group of test users. We're using point source algorithms, so you can already see there's a problem. So we are equally limited in that we treat earthquakes as point sources, and that's okay, up to about a magnitude 7. Once you get above a magnitude 7, it's a real problem. But we are running this California-wide, and it soon actually will be West Coast-wide. So how does the system operate? I mentioned the stations that Berkeley runs, but this is a collaboration between Berkeley, the USGS, and Caltech. So these are the Berkeley stations that I mentioned. All of their data streams into the Berkeley Seismolab, just over here. The National Strong Motion Network stations in yellow and the Northern California Network stations, there are many more of them because they're lower quality instruments, but they all stream into the USGS in Menlo Park. In Southern California, the network is jointly run by Caltech and the USGS, and the data all streams continuously into Pasadena. So we have 3 processing centers here at Berkeley, USGS Menlo Park, and the Caltech Pasadena office. So 3 locations where we need to be processing the data in real time, combining the information, and generating our alerts, and then we're pushing these alerts out to this group of test users that I just mentioned. So I'm going to show you what this looks like. Right now we have a demonstration app that you can use to get the alert. It's called the user display, and it's a Java application that you run on your desktop computer. It connects to the system over the internet, and whenever there's an earthquake, it pops up and it tells you what it means for you.
Earthquake, no. Shaking expected in 19 seconds. Earthquake, no. Shaking expected in 12 seconds. Earthquake, no. Shaking expected in 5 seconds.
Now I'm showing you this particular event. It's a small event. It's only a magnitude 3.5 earthquake. But the reason I'm showing this event is that the epicenter is very close to the epicenter of the Loma Prieta earthquake. Of course, that was the last major damaging earthquake here in the Bay Area. And you can see in a repeat of that earthquake, because the timing is the same, irrespective of magnitude, in a repeat of that earthquake, you'd get about 20 seconds of warning. And that's a significant amount of time. Of course, this app is telling you in a very dramatic voice, no shaking expected. Well, of course, for magnitude 3.5, there's no shaking expected here in the Bay Area, in Berkeley. And so that's why it's telling you that. But of course, you can set the threshold. So I have it tell me about every single earthquake that occurs in California. Of course, a regular user would set it to some threshold of felt shaking or something like that. You don't have to get every single earthquake. But the point is that this is an operational system. And to come back, I think you asked the question about, was data important in getting that law passed? Absolutely. Everybody involved in this saw these kinds of demonstrations. And we, of course, have other events in Southern California. So we show the Southern California examples to the Southern California Legislature, et cetera, et cetera. So yeah, absolutely key, I would say. Okay, so now talking about the nuts and bolts and how this system streams all of this data together. We have these three algorithms that are currently running independently. ELARMS, which is the algorithm that we've developed here at Berkeley. Virtual Seismologist, which is ETH Zurich and Caltech. And the on-site algorithm, which is a Caltech algorithm. So these are three independent algorithms that are all running in parallel. They all stream their information about earthquakes into what we call the decision module, which combines the information to provide a single sort of unified output to a variety of receivers. I just showed you the user display. We have other groups. Google, for example, wrote their own API to receive the information and do whatever they wanted to. And of course, everybody wants it on their cell phone. But the point is that this system is being set up in such a way that additional modules can be added. Okay? But this opens up, and particularly now, all kinds of interesting sort of informational science questions about how you combine this information. What is independent information? How do you prioritize the information? It's been fairly simple with these algorithms because they're all producing very similar types of information. I'm going to show you some new algorithms which are providing very different types of information. They are all going to have to be combined in this decision module, and it's completely unclear how we would do that. That's going to be one of the main challenges for the project as we move forward. I'm going to skip over this because this is just some statistics on how it's doing. I'm going to run out of time, and I want to show you. I will pause here because this is our algorithm. And here's the success rate in the San Francisco Bay Area. It's 100% success rate, and in the Los Angeles area, 100% success rate. But we are unfortunately fortunately talking about the statistics of small numbers. Okay, so
that's very important because that's type 1 and type 2 errors. We're talking about false positives, false negatives.
Absolutely.
And I wonder, I vaguely remember the story about the volcanologists in Italy who got in trouble because I think they falsely predicted an earthquake.
Seismologists, yes.
A volcano.
Yep, and they went to jail.
And they went to jail, which
yep.
is sort of stunning.
This is the L'Aquila earthquake I think you're talking about.
Yeah.
That's right. Basically, there was a swarm of events. There was a committee that formed. It was not just seismologists, not just scientists. It was also kind of civil response. And they concluded that there was no scientific basis to expect a larger magnitude earthquake. And then the announcement that went out that was made by the civil protection people rather than the scientists was far too bold. It was go home, drink your wine, there's not going to be an earthquake. And then there was an earthquake. The people who were on that committee were all put on trial, and they were all found guilty of manslaughter, and they all went to jail, including the scientists.
Does that not scare you a little bit? That's scary.
Terrifies my wife. This is actually that. Joking aside, that.
What's interesting is that 6 Italian scientists I actually interviewed at LBL.
Okay.
All said they thought those guys should go to jail, which really surprised me.
Sorry, who thought they should go to jail?
The Italian scientists who work up the hill.
Oh, really?
They just took sort of a very informal poll
Mm-hmm.
and said, "What do you guys think?" And they all agreed that, yep, they're guilty. They failed.
Well, okay.
That was shocking.
So this is not what my talk's about, but we can.
There's going to be false negatives. And
yes.
The question is, How do you protect yourself?
Okay, so the answer to that is the USGS are going to issue the alerts. So the model, and this is actually something that has run into some trouble over the last month, so that's another detail, but the model that we want to follow is the National Hurricane Center. So in that case, it's a federal US agency that issues the alerts. And the idea is that because they have the authority and responsibility to issue alerts, they also then are not liable when they make mistakes. And so that's the model that we want to follow here. And so it would be the US Geologic Survey that would issue the alerts rather than
anybody else. So basically the
else.
government assumes the liability.
Exactly. That's basically the idea. Yeah, that's exactly right.
But it seems another concern is kind of the sampling that's done here, where the sensors are in San Francisco and LA areas. So I think about the politics of Northern California, where 2 counties have actually voted to secede from California, right? It's because they're not getting state services. And here's a good example. And there's that nice cluster of Northern California.
Yeah, it's difficult to see. I hope people can see what he's referring to. So the light grey circles in here are the instruments that are available to us for early warning. It was on the same map that I showed you earlier. And it's very dense around the Bay Area, and it's sort of kind of dense around the Los Angeles area. That's why we've drawn these boxes. That's why in these boxes we do much better, is because we have much denser instrumentation. The cost of implementing the early warning system that the state has said it's going to do is $80 million. And in that $80 million is a big chunk to densify seismic instrumentation. And that's particularly important here and here. You basically want to have dense instrumentation wherever there's a fault. So as I said at the very beginning, you get the most warning when the earthquake starts up here at the northern end of the San Andreas Fault and ruptures down towards the Bay Area. But to get that warning, you need dense instrumentation up here, and we currently don't have it.
Is there a way to have the end user be the one that makes the decision about the type 1, type 2 errors that they're willing to receive, in the sense that, if I never want to miss an earthquake, I can just get all of them, and I just understand that I'm really willing to have a lot of cry wolf happen to me.
Right.
Or I could dial the other direction.
Yeah. So the user display that we have right now, again, it's not really intended to be for the public. It's intended to be for people working on the project. But there are various things that you can set. You can set your threshold in terms of the magnitude, the shaking intensity at your location. You can also set it in terms of the certainty. So we also have a likelihood parameter. So every alert that goes out has a likelihood associated with it. And you can set your threshold. So that's kind of the threshold that you're talking about now. Having said that, how accurate our likelihood values are is a real problem. And so the concept is there, but on that particular case, we need to do more work on our end of things to come up with what are really good likelihood values.
Likelihood is whether it's detected or not, whether it's real or not one?
Yes. Yeah.
Repeat the question.
So the question was whether this was the likelihood that it's a real earthquake or not. And yes, that's what I mean by likelihood. There is also an uncertainty. There are also uncertainties in all of the parameters, the magnitude, the location, the origin time as well. So we have all of those values. We have placeholders, I think is the best way to call it. We have numbers in them. We have what we think are the best numbers we can generate right now in them, but I'm sure we could do much better.
How about, is there a threshold or the distance? So when you have the alarm going out with the no shaking expected, could you have options to have a notification when you expect shaking?
Yeah, oh, absolutely. So that's the threat. So there are several. So one of the thresholds is. So let me back up a second. So everybody knows what earthquake magnitude is, but magnitude of an earthquake really doesn't matter to you. What you care about is how strong is the shaking here. So one of the thresholds you can set is the strength of shaking at your location. Yeah.
When you go live to the public, do you have a spec for what level of false positive and negative you think is politically viable? Like, you can't get it wrong too many times before they pull your funding.
Yeah.
So
Yes,
what's the goal here?
Yeah. This is. Okay, so I can see the figures I was going to skip over are probably the most important to this group after all. So let me show you this. Okay, so these are the 3 algorithms that we're running. Okay, so the on-site algorithm, the ELARMS algorithm, the VS algorithm. Shake alert is the overall output of the system. Okay, and so what's actually shown in these histograms is the time at which the alert goes out for a whole bunch of earthquakes. So you can see that the on-site algorithm is the fastest, right? It's furthest to the left. The ELARMS algorithm is in the middle, and then the virtual seismologist algorithm is to the right. Okay, so this is the fastest, this is in the middle, this is the slowest. All right, and then you go and look at the uncertainties. The on-site algorithm has by far the largest uncertainties. Okay, so the magnitude uncertainty is plus or minus 0.7 magnitude units compared to the other two, which is 0.3, 0.4 magnitude. So it's twice as the uncertainty is twice as large. Same for the origin time and the location. The reason is that the on-site algorithm is specifically designed to be as fast as possible. It actually only gets data from one station, and then it looks for a trigger at a second station, and then it pushes out the alert. So it's the fastest, and it's also has the largest uncertainties. The virtual seismologist is the most robust algorithm. It has the fewest false and missed alarms. However, it's the slowest. Okay, and so ELARMS, as I mentioned earlier, that's our algorithm. So we're trying to strike the happy medium. We're trying to answer the question that you just asked of where do you want to be on this scale from fastest to most accurate. And in fact, we've made some changes where, in fact, ELARMS is now almost as fast as on-site. Often it beats on-site algorithm while still being as accurate. So that's one answer, is to try and find the right balance. But still there's going to be this question of what alerts you push out to the public. How likely do you want the event to be before you push it out in order to not have too many cry wolf type situations?
Do you have a number that you're aiming for?
No. Better. I mean, it's also more complicated because, so you can think about the public user, and maybe there's one answer for the public. But there's all these sophisticated users, people like, well, PG&E, Chevron, BART, people who have an understanding of seismology, of earthquakes, who have people on staff that worry about these things and are actually able to digest much more sophisticated information, including these uncertainties. And then maybe they want the full stream, and they are going to choose where their threshold is, and they can choose it in an intelligent fashion. Whereas perhaps if you put out the whole thing to the public, people are not going to be in a position to do that.
And I would mention that all of these algorithms, in some sense, are screening of the alert you showed. It seemed like once the alert was sent, there's like no turning back. Whereas some you made 5 seconds later say, I update it.
Yeah.
It's, going to be stronger than I said.
That's right. No, these alerts, they do update. That's right. So we put out a first alert. That was the previous figure that I skipped over, in fact. Oops. So this doesn't really show it very well, but this is actually a timeline for a particular alert, for a particular earthquake. 0, this is 50 seconds. So this is the origin time of the earthquake. The different lines here, this is actually the magnitude estimate. The dashed line is the correct answer. And then the different colored lines are the different algorithms pushing in their information. And then the red line is the overall output of the shake alert system. And so you can see the blue comes with the first information. That's actually the on-site algorithm. The green is the ELARMS algorithm that comes in, I'm going to guess, a second later. And then virtual seismologist is 2 or 3 seconds after that. And so you can sort of see how the estimates of each of the individual algorithms and the overall estimate is also changing. So this is a continual stream of information that's being updated. You can also see that the on-site then triggered our second time and thought it was a separate earthquake, but then deleted it. So there, you can cancel a message. And this is another area that is debated. How valid is it to cancel an event? I.e., if you're going to push out an alert, and then you say, oh, you know what, we were a mistake. 3 seconds later, you say, sorry, our mistake. Well, how's the public going to view that? I mean, the public's not going to say, oh, that's not a false alarm because you cancelled it 3 seconds later, right? From the public standpoint, it's a false alarm for sure. So these are the kinds of issues that we have to work our way through. Yeah.
Just to understand the difference between the Italy case and this, that was there they weren't worried about real-time early warning. That was kind of like a day-ahead prediction.
That's right, earthquake prediction.
You guys are not getting into that business, at least not here.
No, we're not getting into that business, period.
Okay.
Yeah.
You're only looking at real-time early warning.
Yeah. The difference, just to be clear, the difference between earthquake prediction and what we're doing, earthquake prediction is predicting when an earthquake is going to nucleate on a fault. That's a completely different problem, and we can't do that. This is, of course, the earthquake has nucleated on the fault, and we are just detecting it, and we are estimating how big it's going to become and what the shaking is going to be.
And they were burnt at this stage because they made a call on that.
Yeah.
24, 48 hour ahead non-nucleation.
Yeah. Yes, that's right. They were right. What they said was correct. There was no scientific basis to expect another earthquake. But you never say there's not going to be an earthquake, because there can always be an earthquake. That was where they made their mistake. Yeah. Okay. Yes?
I was wondering, just seeing you mentioned a shift in algorithms that you were updating. I was wondering if you could sort of zoom out and sort of, in the past few years, like what have been the big changes that allow us to sort of do this now?
Earthquake early warning generally?
People have cell phones, right? But that's, I mean, the other is that you can aggregate, right? Many more. Is it more sensors? Is it better algorithms? Could you give us that?
Yeah, okay. I'd say it's actually all of the above. So first of all, the science behind this, actually being able to very rapidly estimate the magnitude of earthquakes, that's new science. So there's some new science, some new fundamental understanding of the process here. There's a technology component. The fact that the communications for how we get the data have become much more rapid over the course of the last 5 years or so make this technically feasible. And so the fact that you have this new science and you have that technical communications capability means that we went and developed the algorithms that could make use of it quickly enough. So it's all of those things that have made, there's been significant progress in the last decade or so.
Have you started to incorporate feedback from the community cell phone with these accelerometers?
So, how much time do I have? Well, I have 10 minutes. You know what I'm going to do? So, I'm going to skip, and because I think that's the piece that I think is very valuable to this group. So I'm going to skip over talking about how we're going to detect big earthquakes, which was the problem with the Japan example. Whoops. Oh, that's interesting. How do I get the... Okay. I'm going to skip over I want to tell you that we have a solution for big earthquakes, i.e. the problem that they had in Japan. We now have a solution to that. And I'm going to very quickly just give you kind of an overview of what we're trying to do using smartphones. So this is this network of 400 instruments that I just talked about that is part of the real-time system today. But if we wanted to kind of go the next generation of instrumentation, then maybe we would be looking for some kind of network like this. This is a really remarkable, this is not cell phones, this is a deployment of geophones that was done in Southern California. This is Long Beach, over an area 10 kilometers by 7 kilometers, 5,000 geophones. This was actually for oil exploration. And what's even more remarkable is that they then shared the data with us as well. And so this is work that Chinkai, who's here, has been doing. And so this just shows the seismic energy radiating across this array from a small earthquake that was close to this array. This is actually one of the faults. This is the Newport-Inglewood fault that runs through Long Beach. And you show this to seismologists and they start drooling. There's so much that you can extract from this data set to do with all aspects of seismology, source studies, structural studies, and of course you could also use this for real-time information to really have much more accurate and much more certain earthquake early warning type of studies. So how do you do this? How do you get a network that is something like this? Well, of course, the idea of using the accelerometers in smartphones is one possibility. I don't need to explain why smartphones might be able to do this, but the real challenge is then, how do you get the data? How do you process the data? What can you do with the data? How good's the quality of the data? This is the big data challenge for us in seismology. We need an app to collect the data. We need back-end servers. And then the exciting part is we can do the development of the both science and societal applications making use of it. The potential here, of course, is huge. The number of smartphones in California is about 16 million. We're using 400 stations for today's earthquake early warning system. So this is many, many, many orders of magnitude. But also when we look globally, we can do early warning in California. California has one of the densest seismic networks. If we wanted to do early warning in other regions, then we might be able to do it if we're able to harness these kinds of instruments. And then, of course, you can do 3D monitoring, right? People have cell phones on every story of a tower block, and so you can actually see how the entire tower block is moving during earthquakes. And so we have a collaboration with Deutsche Telekom, and in fact now also with Sense Systems, who do back-end server type stuff, to build an app and to start to test it. We've done some initial efforts to collect data and sort of do feasibility type studies. collecting continuous recordings, and of course also collecting the equivalent of earthquake recordings. So this is Chinkai's setup on a shake table, about 20 phones I believe he had for this particular test. And just to give you a sense, we were doing this out on the shake table, Pia's shake table out in the Richmond Field Center station. And this is what they're actually testing. I mean, they build buildings on this shake table, and then this is our 20 phones on the little corner. Chinkai has to do this at the last minute, just before they do the test, because nobody notices these. They just walk all over them if he doesn't do it at the last minute. So this is some of the challenges of collecting the data. But so are we going to be able to detect earthquakes with these? Of course, the quality of the sensors in these things is nowhere near the quality of the sensors in the rest of our networks. But we believe that you can. And so this is a plot. This is amplitude, frequency content. These dashed lines are the typical amplitudes for different magnitudes of earthquakes. These colored lines are the various cell phones that Chinkai was testing. This is a noise floor test. And what you can see is that the noise floor of the cell phones is kind of just below a magnitude 5.5 earthquake. So using today's earthquakes, using today's phones, you could detect an earthquake magnitude 5 within about 10 kilometers. So that's okay. I mean, of course, we only care about big earthquakes, but if you want to be able to do things with this, you need to be able to collect a lot of data. So we would like the instrumentation to improve, and of course, it is improving. This is the latest HP MEMS sensor. This is a very expensive sensor, but on a chip. That's not going to end up in cell phones, but this is down in what we call the below the high noise model. So this is down with the kind of sensitivity as some of our observatory standard equipment. So we expect this to come down. So while we can detect magnitude 5 earthquakes today, it's not unreasonable to imagine that we could detect magnitude 3 earthquakes at greater distances in the future. The frequency response of these, the current accelerometer is great. It's in the same frequency response is great in the same range of what does damage. So for hazards, it does a good job. We can also do a very good job of distinguishing earthquakes from people jumping around, riding on BART, on buses, whatever, separating out the everyday jolts that phones get from earthquakes. This is some work of Chinkai's, again, separating out non-earthquake signals from earthquake signals by identifying the key characteristics. And this is just doing this on one phone. Okay? And his success rate is remarkable. More than a 99% success rate of separating out an earthquake from a non-earthquake signal on a single phone. So now,
how long of a
2
chunk
seconds
of data is needed for that accuracy?
2 seconds.
If you need 5 minutes, 2 seconds
Yep.
is enough to get 998. Wow, that's
Yeah. It's very encouraging, right? And but what's really important here is this is on a single phone. So now imagine you build the system and you're collecting the data from multiple phones. Of course, you would expect, I don't know how many there are in this room, but there's probably at least as many as there are people. So you would expect to see multiple phones seeing the same signal, and then that gives you much more confidence. So again, these are all reasons why we moved on to the phase of actually implementing this. This is just kind of, I'm going to skip over this, but this is just to show how that kind of works. So where are we with this project? And then I'm going to stop. So we've gathered this initial data. We're pretty convinced that we are going to be able to record earthquakes with the accelerometers in phones. Can we distinguish them from other signals? Yes. So we're currently getting very close, as in a few weeks away, from rolling out an app that we're planning on rolling out on campus. It's going to be called MyShake, a project called MyShake. And so our plan, we now have an app and we have a back-end server, and the plan is to use campus and try and generate some interest in this on campus to roll out this app to start collecting some of the data. So
3 versus 5 magnitude, usually the current accelerometer.
Yes. That's right. So today we could do magnitude 5. So we're then going to be hoping for a big earthquake on the Berkeley campus. But yeah, when I say magnitude 3, I mean that's at some point in the future. That's right. So we expect to have this rolled out, hopefully to a few thousand phones this year. And that's, of course, when the exciting part of the science starts. So where are we in terms of our overall outlook for earthquake early warning? Well, today we have this demonstration system. We're migrating into what we call our prototype system, which is a blueprint for this public system that the state just ordered. So we very much want to get to that point as quickly as possible. We've already talked about the state support. We actually also had significant support in Washington, D.C. as well. In fact, we had the California delegation on the House Appropriations Committee was ready to write into House Appropriations this year the funding to build a West Coast earthquake early warning system. So that was obviously a really big deal. And then, of course, the whole thing went into suspense. So we're all over for another year, not to mention what's been going on since. In terms of the global outlook, I skipped over this, but there are good networks in some places, but not in most places. And so our hope is that we can start to make use of these accelerometers in the smartphones in order to fill that gap. All right, I will stop there, and I'll answer any other questions.
Thank you.
So thank you, Richard. We have time for maybe one or two quick questions, but before we do that, I just wanted to mention two things. Number one, if you're interested in hearing about these lectures as they come up and other big data science news on campus, please send an email to datascience@berkeley.edu and get yourself on a list. And second of all, the next one of these lectures is going to be October 17th, where Bin-Yu will be talking about the work that she's done in statistics and sort of marrying that to some really interesting problems in neuroscience. So with that, let me just sort of take one or two more questions, try to be respectful of everyone's time. So go ahead.
I was curious about how much of the work is the domain science aspect versus the big data aspect of a million phones calling some server saying I see an earthquake, versus stupid stuff like different sensor networks are owned by different people who don't want to share their data or have different protocols. Where do you spend your time on this?
Yeah, so obviously I'm entirely a domain scientist, right, at this point. The way we've been dealing with, this is kind of why we've sort of gotten engaged in this data science kind of effort here on campus, is that we have been doing this pretty much entirely within the Seismo lab, so a bunch of domain scientists. For this project, of course, we have to start going beyond that. The technical side of this project is entirely being done by our partners. So Deutsche Telekom are generating the app, Sense Systems are doing the back-end server, and so then that just leaves us to do the actual data processing, the seismology part, what we think of as the seismology part of the problem. But clearly there are opportunities to go far beyond that. The way that we do seismology as a whole, the way that we separate out the signal from the noise in that plot that I showed at the very beginning, is based on techniques that frankly we started to develop in the 70s. And so I think that there's a real opportunity to go and apply much more modern techniques to extract the data to the entire seismic data set, not just the smartphones, but the entire seismic data set. So that's why I wanted to plug the NCEDC as being a good source of data to do that.
Last question here.
So I can imagine the apt data sets being extraordinarily interesting for the public to access in many ways and for people to track their algorithms. I can see a number of reasons why it would be very interesting and valuable to have access to that data, but the privacy implications of that are pretty severe, right? Because this is data that is actually very accurately geolocated, and no matter how you anonymize it, de-anonymizing that data set for someone who's interested in tracking someone would be trivial to do.
Yeah.
How are you guys dealing with that aspect of data into the public?
Right. So I don't know how to answer that. One answer would be that we're not worrying about it. That would perhaps be the most truthful answer. I can tell you that we've had, I think we're up to 4 companies contact us that want to engage with us on this project. And they are companies that are willing to put in their support because they want access to the data. So they see, so we're the idea that you're doing this to collect data for earthquake studies, it gives the reason for doing this, but at the same time they're very interested in looking at the data for, to see whether somebody's, what they're doing so they can sell something to them, basically. So this is a problem that we, for our initial testing, what we're going to simply do is that the app will say, can I use your data? And you either say yes or no, and if you say no, then you're just not part of the experiment. So we're still not worrying about that. But if you wanted to go to the point that I'm talking about, then we have to start to worry about it. But I don't want to worry about it.
I think we've got to cut it off there. Let's thank Richard again for a great talk. And thank all of you for coming. Hopefully you'll be able to stick around for a little bit, answer a couple questions. Sure.